In today's class, we are going to have a short discussion on cope rearrangement, one of the type of sigmotropic sets. In the previous class, we have completed our sigmotropic reactions. So, in today's class, we will start with examples of sigmotropic reactions. One of the most common examples is cope rearrangement. Cope rearrangement is basically it exists where we have a 1,5 diene system. 1,5 diene system, for example, like this 1, 2, 3, 4, 5, 6. There are two double bonds, that is a diene system. The position number 1 and position number 5 is having a diene position. While studying pericyclic reactions, what we need to have is first the identification of the system. Identification of the system, that means it involves how many pi electrons are involved in that. So 2 pi electrons from this, 2 pi electrons from this, and this sigma bond is also going to take part in that. Therefore, the 2 electrons will be also counted from this place. Therefore, there are total 6 electrons, and for 6 electrons, we need to follow 4n plus 2. We have to say that this system is going to follow 4n plus 2 pi system. So, what are the main features of cope rearrangement for writing short notes or for writing an described answers? In case of this cope rearrangement, we need to focus on some taglines, some specific lines which we need to have to give an explanation in our answer. First thing is the bond between C3 and C4 carbon atom is going to be broken. The cleavage of this C3 and C4 carbon takes place. The formation of bond takes place at C1 and C6. Since this is an example of pericyclic reaction, therefore, we already know that pericyclic reactions occur via concerted mechanism. Concerted mechanism means bond breaking and bond formation will take place simultaneously. So, we can easily say C3 and C4 bond will break at the same time. C1 and C6 bond will be formed. So, this cope rearrangement will occur through this concerted mechanism, having a transition state which involves a 6-member transition state with via a 6-member transition state. This type of a rearrangement is a class of sigmotropic reactions which is named as 3,3 sigmotropic rearrangement. Why it is 3,3 sigmotropic rearrangement? Since if we'll count the position of the new bond formation, that is the destination carbon atom, this is 1, 2, 3 and 1, 2, 3. One of the allyl group is going to migrate and the new bond is going to form over here. Therefore, this is called a 3,3 sigmotropic shift. That was about the name of the type of sigmotropic reactions involved in this cope rearrangement. Again, we have to focus on the main point that this sigmotropic 3,3 rearrangement, which is cope rearrangement, is thermally allowed process. I'll explain how we can predict that this is a thermal allowed process or a photochemical allowed process. Already we have discussed the selection rule regarding this. The driving force for the formation, the driving force for this reaction to occur, why this happens, this bond breaks and this bond is formed, is basically the formation of a more substituted CC carbon double bond. And as we know, the more substituted dienes, more substituted alkenes are more stable than less substituted alkene. In the previous lectures or in the syllabus of the BSc, we have a part that stability of alkenes. That stability of alkenes is on the basis of number of hydrogen conjugated structures. That is other part. We'll discuss it sometime else. Since that I have already explained, it involves a 6-member transition state. Now the question arises, how this takes place? This bond comes from this place to this place and a new bond is formed between this 3,3 carbon atom. This bond will shift over here to generate a double bond over here, a double bond over here and a new bond. So this bond, the old sigma bond, which is going to be cleaved, and this is the new sigma bond which is going to be form through a concerted mechanism which involves the cyclic transition state. This cyclic transition state is the intermediate cyclic transition state. Now, what I was discussing is about a trick, that is how can we identify, since we have learned the selection rule in detail in our previous classes, but still, how with the one chance we can easily we can see it, what type of system it is, and is it thermally allowed or is it a photochemically allowed process. In that case, what I think is we need to count the number of arrows. You count the number of arrows. How many arrows are involved over here? Arrows which are indicating the migration of pi electrons. So, what are the number of pi electrons? What are the number of pi electron? The arrows involved in pi electron? Odd. 3 arrows are involved. 1, 2, 3. Odd arrows to show migration. See, sometimes it happens that we had only 2 arrow or 4 arrow. The even arrows are formed. If it is an odd arrow, then the system will involve 6 electrons. 4n plus 2 system. 4n plus 2 system. It means it is a 4n plus 2 system. It will be thermally allowed. And if the number of arrows involved they are even, then it is photochemically involved. Even arrows indicates photochemical. That is not a rule. That is basically a trick. You count the number of arrows. If there are 3, 5, 7 arrows involved, then that will be thermally allowed process. And if the number of arrows are even, then that will be a photochemically allowed. This is not a rule. This is not a selection rule. This is not a proper explanation for the selection rule, but it's a trick. It will give you the answer, exact answer to predict the stability. Let's apply the concept of 3-3 sigmatropic shift in one of the question. The main thing is in net and different type of competitive exams, the question that does not directly comes from a single concept. It involves more than one concept. Some concepts are from the reagent part and some concepts are from the other parts of the organic chemistry. In this case, they are involving two concepts. In the first part of the question, this is the main question. In the first part of the question, they are involving the concept of reagents, that is Hofmann exhaustive methylation is being used. And after the Hofmann exhaustive methylations, we know the product is always an alkene. So, a diene will be formed, and in that diene, thermal condition indicates that this is going to be a 3-3 sigmatropic shift. That is an example of Cope rearrangement over this place at the third step. So, what we have learned today is Cope rearrangement. That Cope rearrangement may be asked as a part of some questions in section 3 in CSIR net exams or directly in your annual exams involving them, the type of the sigmatropic shift with other concepts of the reagents what you have learning in the other part of the syllabus, that is reactions and reagent mechanism. So, in solving this, in the first part, by seeing this word axis, we can easily think of that this is going to be a case of Hofmann exhaustive methylation, in which this nitrogen at the position number 9 methylation will occur. Then, since methyl iodide is present in excess, this methyl iodide, the second molecule of the methyl iodide is also again going to be added at this position number at this position nitrogen. So, we are going to have a tertiary ammonium salt present over here. This condition of Ag2O generates a basic condition which can abstract a proton from where it gets to form an alkene. This is the alkenes are the major products in case of Hofmann exhaustive methylation. So, this will generate the abstraction of a proton from this methyl group will generate a primary carbon ion. Therefore, the preferred position is this. The most stable carbon ion is generated. This position, this OH will take a proton from this CH3 as shown in this step, and the migration of this negative charge will attack over this to generate a positive charge over here, and the the migration of this, the breaking of this bond because of the electronegative nature of a positive charge heteroatom. What we can easily think from the concept of the electronegativities and the comparative relative electronegativities, if a electronegative atom is bearing a positive charge, then it becomes more dangerous, and then there are comparative or relative more electronegative atoms also. Therefore, this nitrogen will break this bond, and we get a alkene over here. Since as in the previous case, still there are lone pairs of electrons on the nitrogen atom. Therefore, Hofmann exhaustive methylation will not stop in the first step. Still, this nitrogen can be methylated since we have used excess of methyl iodide. So, this nitrogen again comes into the play to have to attack on this, and therefore 3 methyl groups will be attached with a positive charge over there, as explained in the mechanism here. Then in the final step of Hofmann exhaustive methylation, we were already having an alkene at this position, and alkene will be generated over here. In this elimination process, we'll be having a double bond over here by the migration of this bond, or by the breaking of this nitrogen carbon bond, and this will be satisfied by the rule of this aqueous medium, the basic medium present generated due to this aqueous Ag2O. This OH minus will take a proton from this place. This bond will migrate here to generate a positive charge over here, and the double bond over here. So this is going to be the product which we are going to use for the co-rearrangement with the byproduct way of the Hofmann exhaustive methylation reaction. This is for reaction, as we know, the 1,3,1,5 diene must be in a cis-oid form to approach each other. The p orbitals, the terminal p orbitals will always approach if they are close in the vicinity, or otherwise the reaction is not possible. Therefore, we have written this alkene diene like this. To understand the co-arrangement, I have just shifted it, I have just rotated it to have a clear look of the 3,3 sigmatropic shift. This ME position will come here and with these double bonds. Now you can easily see this 1, 2, and 3. 3 arrows thermally allowed, 3 arrows, this is thermal condition. 3 arrows thermally allowed, and the position 1, 2, 3, 1, 2, 3. Therefore, this is a 3,3 sigmatropic shift to generate a product. So we can easily see the first part was involving a reagent part, reaction mechanism part, and the last step is involving a co-arrangement, that is a part of the pericyclic reaction.